Hi everyone. In the previous video I told you two methods of computing the mean and the standard deviation, two different ways of getting the same result. Let me do the third one so that it's your personal choice. Whatever the method you like, you prefer, it's your personal choice. The third method is you go to the formulas. Let's say you click your cursor here and now you go to the formulas and you go to the more function and you go to the statistical function. Now when you go to the statistical function, all the functions are arranged here. So look at this function. The first one is the average. You click on this average. Now the Excel is asking, okay, where is your data? So he's asking number one mean, where is your data? So you give the Excel the range here and press OK, and the answer will appear here. Same answer as we did previously. Now I show you how to compute the standard deviation. Same thing, you go to the formulas, you go to the more function, you go to the statistical function. Most of the functions are here written in alphabetic order. So we are looking for stdev. So you scroll down and try to find stdev.s. We're doing the sample calculation. We're doing the calculation for the sample data. So this also there is the S here, right? So you the stdev.s. You click on that. Now again Excel is asking where are your numbers for which you want the computation. These are my numbers, and you press OK, and you will get the answer, right? So that's the third way of computing the same result, right? So I told you three methods of doing the same computation. It's your personal choice, whatever you like. Now to extend our discussion, let us suppose we have a two data set, right? The data set 1 and a data set 2, and we want to compute the mean and the standard deviation for the data set 1 and the data set 2. I ask you guys to pause this video and tell me what are these numbers by using Microsoft Excel. So clearly this is what we have already done. X sample mean, X bar, which is 50.0, right? X bar, which is the sample mean, and S is equal to the sample standard deviation is 14.2. This the calculation which I showed you earlier, right? And I hope you get the same answer for the data set 1. Now what I want to tell you here, let's draw a dot plot. Let's draw a dot plot. So let's draw a dot plot for these two data sets. Look at the dot plot 1 and look at the dot plot 2. Clearly, you see both data sets have the same mean. Both data sets have the same mean. Mean is 50, mean is 50 here. But look at the standard deviation for the first one 7.4 and for the second one 14.2. Clearly, all the data values in this here are green. Look at these, how they are clustered around the mean. And here, all the data values are clustered around the mean. If you pause this video and think about this question, that in which dot plot there is a more spread in the data and why? In which dot plot, I repeat the question, in which dot plot the green dots are more spread around the mean? Is it the data set 1 or is it the data set 2? Pause the video and think about it and think the reason about it. And clearly you see there is a more spread, the green dots are more spread in a data set 2 as compared to the data set 1. And the reason is this one, the standard deviation. The standard deviation is 14.2. Here the standard deviation is 7.4. Almost double, not exactly the double, almost double, right? It's almost double the standard deviation. So what happened? The rule which I want to tell you is larger the standard deviation, larger the spread is. The smaller the standard deviation, the smaller the spread is. This is one of the things you can see. You can see physically the effect of the standard deviation. Larger the standard deviation, larger is the spread. Smaller the standard deviation, smaller the spread. Another important thing which you would like to note here is almost all the data values are within within these two walls. Let me write these two walls. Let me point out these two walls. Okay, this is the wall. This is the first wall, and this is the second wall, right? All the data values are within these two walls. Again, look at that. This is the wall, and this is another wall. Think like it's not physically a wall, but just I'm telling you, right? So all my data values are within these two walls. And what are these walls? These walls makes you 3 standard deviation from the mean. What happened? You are here, and you jump 1 standard deviation, you reach here. You jump another standard deviation, you reach here. You jump another standard deviation, you reach here. Now from here you add a standard deviation, and here if you want to go in a backward direction, you subtract the standard deviation. Like this, you subtract, you get like this. You subtract, you get like this. So all my data values are within the 3 standard deviation, and this is the rule which I'm about to teach you. And the rule says almost all our observation are within the 3 standard deviation on either side of the mean. Almost all my data values are within the 3 standard deviation. Almost all the observation. But this word almost all is ambiguous. This word is not clear. What do you mean by almost all? So when I say almost all, this is not clear. In order to remove this ambiguity, we define another rule which is called an empirical rule. And this empirical rule tells you that, and this empirical rule is applied to a special distribution, a distribution which has a special shape, and that is approximately a bell-shaped distribution. I hope you remember what was the bell shape, right? The bell-shaped distribution, I hope you remember that. This was the bell shape, like this. This is the mound shape or a bell-shaped distribution. So this is applicable. You can apply this rule, this empirical rule, to a bell-shaped distribution, right? And what this rule says, it says that 68% of all observations lie within 1 standard deviation on either side of the mean. 95% of the values lie within the 2 standard deviation on either side of the mean, and 99.7% of the observation lie within the 3 standard deviation on either side of the mean, right? When I read this, you probably won't understand, but I have to show you the picture, and then probably you will better understand. Let's see the picture. This picture makes it clear. I hope. Look at that picture. This is one. This says that almost 68% of the values are here. These 68% of the values are here in this ring, and this is the 1 standard deviation. Look at this is my mean, and this is the 1 standard deviation on this side, and the 1 standard deviation on this side. And the rule says 95% of the values are in this range. On 95% of the data values are within the 2 standard deviation. How 2 standard deviation? Look at that. 1 standard deviation and a 2 standard deviation. And same, you subtract 1 standard deviation and another standard deviation, 2 standard deviation. And 99.7% of all your observation lie within this range, right? 99.7% of your observation lie in this particular range. So please don't get confused when I'm writing this. When I was doing the graphing, I mean this. I was trying to show you. I marked the page with a different setting. Actually, it's this, and 95% are here, and 99.7% of your values are here. Right. So this is the rule which is called the empirical rule, right? And you need to understand this, and you need to remember this. And this rule is also called, some people also call this rule as 99 68, 95 and 99.7% rule. Due to this rule is also called like this. How we're going to apply this rule, how we can understand this rule, let's see an example. So the example is the mean IQ score of adult is 100 with a standard deviation of 15. Use empirical rule to find the percentage of the adults with a score between 70 and 130. We assume that the data set has a bell-shaped distribution. Now this is important because we are already told this is a bell-shaped distribution, and as this is a bell-shaped distribution, we can apply our empirical rule. Remember, the empirical rule is only applicable if we have a bell-shaped distribution, if the shape of the distribution is somewhat similar to a bell shape. If it's any other distribution, the shape is not a bell shape, you cannot apply the empirical rule, right? This problem can be solved by using multiple different ways, but I try to give you the easiest of the way, right? What you do, you draw a straight line, and exactly in the middle you write the mean value, which is 100. Write them, that's a mean, and you write the standard deviation. Let's say this is the mean, mu, this is the Greek symbol mu for the population standard deviation, and we have sigma, the standard deviation for the population. It's equal to, let's say it's 15. Now what you do, you add in 100 of 15, you land at 115. You add another 15, you land at 130. You add another 15, you land at 145. Now in order to go forward you add, in order to go backward you need to subtract. Subtract from 100 of 15, you end up 85. Subtract another 15, you end up 70. And subtract another 15, you end up at 55. Right? So now he is asking what percentage of our data values are between 70 and 130. Look at that. This is 1 standard deviation. This is 1 standard deviation. And here, this is the 2 standard deviation. Look at that. This is the 2 standard deviation. And this is 3 standard deviation. And now, since this is a bell-shaped distribution, we can apply empirical rule. Empirical rule says that 95% of our data values lie within the 2 standard deviation, and our 2 standard deviation are from 170 to 130, right? So we are going to say the 95% of people have IQ score between 70 and 130, right? So I hope you understand the problem. This is very important that you understand this use of empirical rule. It will be applied in the future chapter. The concept will be applied in the future chapter. So if you have any question, write me an email. Thank you very much.